All right, welcome back to the second podcast of week 7, Chem 20. And we are on to our next review section, which is on balancing chemical reactions. Honestly, these are one of my favorite parts of chemistry in general because they are little puzzles, right? So I always like puzzles. They're things where there's not a whole lot you have to memorize. You really just have to play around with things. And anytime in my brain there's less memorization, things just got a little bit easier. So let's chat about how this works again, guys. Ultimately, every chemical reaction involves simply rearranging the different atoms. Now, the key thing with a chemical reaction is that you are not God. I hate to break it to you, but you cannot destroy matter. It doesn't happen. So basically, what you go in with, you have to come out with. And if you don't balance it properly, then you are fundamentally breaking a law. You cannot destroy things. They will still exist in a different format. Now, ultimately, what that means is the total number of each type of element must be exactly the same after the reaction as it was before, which means it's a pretty easy double check. If you start with 4 carbons, you have to finish with 4 carbons, etc., etc. Okay, let's start looking at this. This is the example that's in your notes. And I like this one because you can see that obviously we've got different stuff going in than coming out. For example, we start here, and this is methane, the CH4. And if you look, the carbon is the black in the diagram there, and the hydrogens are white. And we combine that with oxygen. Now this one already is balanced out, so we're combining this with O2. This is super important, guys. Oxygen is diatomic. If you just wrote it as O, as a singular, you're going to get this seriously wrong. So definitely watch for that. Notice, please, that if you forgot what those are called, that 2 in front is called a coefficient. And it means that we don't have just 2 oxygens in general. We have 2 times 2, right? Think about this. So we actually have 1, 2, 3, 4 oxygens in total. Oh, so take note of that. There are 4 oxygens reacting. Consider too, when we go back to those hydrogens, we have 1, 2, 3, 4 hydrogens in total reacting, and we have a single carbon. If that one goes into the reaction, the identical thing has to come out. But notice it's been rearranged differently. So we're now producing carbon dioxide, which is definitely different, and it contains 1, 2 of those oxygens. Well, where are the other 2? Ding, ding, ding. That's when we get over here to the lovely water. Notice once again, we've got a coefficient coming in there. We need to have 2 waters that are being produced. Otherwise, this wouldn't be balanced. So that accounts for 3, 4. Now we've got our 4 oxygens again. How do we get our 4 hydrogens? Oh, they're on the 2 separate waters. 1, 2, 3, 4. 4 hydrogens, and we still have our singular carbon. Check it out. The total atoms that are reacted are the exact identical total atoms that are produced. That's how it works, guys. There has to be the same stuff going in as coming out because you, folks, cannot create or destroy matter. You don't have the capability of that. All right. Now, that proper balancing ultimately comes down to this, the law of conservation of matter. There has to be a proper balancing so that this law is obeyed. Remember, when it comes to science, theories are a big deal. Theories take multiple experiments to develop, and everything about a theory has to match all experimental evidence. While a law is a serious step above. A law in science is something that is completely unrefutable. It is absolute. Think the law of gravity, folks. So that means this law of conservation of matter is a big deal. In other words, the total mass of the products is always exactly the same to the total mass of the reactants. And the diagram that I just showed you here below is just saying, hey, if I take 32 grams of sulfur and I react it with 56 grams of iron, I don't end up with sulfur and iron. Instead, I have a new substance called iron 2 sulfide. But the total mass of it has to be 32 grams plus 56 grams added together. In other words, 88 grams. You cannot destroy matter. It always has to be accounted for. Okay, let's continue on here into some other reminders to you for how these chemical reactions are written. First things first, every chemical reaction has to be written so you have correct formulas. And those correct formulas, guys, absolutely need to take into account the charges being balanced, having correct formulas in terms of making sure you predicted the solubility correctly, you predicted the state of matter correctly, making sure that if something is diatomic, you're showing it, right? So there's a lot of little things, little details that still are really applicable. So for our elements, of course, solid, liquid, or gas, you can see this right on here. So if you look at this, there's that little cheat sheet that is right here, right? So look at the colors to help you. So it shows you on the periodic table if it's a solid, if it's a gas, or it's a liquid. Use that to guide you, please, right? They are on the periodic table. When you're dealing with molecular compounds, it really varies. Some of them are familiar to you, like take carbon dioxide. You should know that's a gas at room temperature. It's very familiar. Take, for example, glucose, sugar, C6H12O6. Well, it's a solid. Of course it is, a sugar. Take water. Water is a liquid at room temperature. So I would expect you to know those ones, guys. When you get to ionic compounds, these ones are a little more complicated. If they are in solution, if they are, you have to look at the solubility table. But now this is potentially new to you, and memorize it, please. If there is no water present and it's room temperature, they will always be a solid. Okay, that will come into play. So again, that's for ionic compounds when there is no water. I already mentioned coefficients with that example right at the beginning of balancing. Now the coefficients are key because we multiply them by the little subscripts. And we'll talk a little bit more about that as we continue with balancing. Do remember, please, though, those coefficients are always the simplest whole number ratios. In other words, you are not using fractions, please. You are not using decimals. And if you can reduce it, you should. Okay? All right, let's continue. A few hints for you to help you with your balancing. Again, this is review. This was fully covered in Science 10. I'm simply reminding you of it. We are going through it again because it is important. Okay, first hint to you is based upon that conservation of matter. The exact same number of each atom must appear on either side of the equation. So for instance, if you have 4 sodiums going in, you'd better have 4 sodiums going out. Remember what I said about multiplying, guys? This is actually 2 times 2, which is 4 sodiums, right? So that coefficient multiplies the little subscript. Similarly, if we have 2 oxygens going in, we have to have 2 coming out. Is that true in this case? Yeah, for sure, because this 2 is going to multiply the invisible 1 that's by that oxygen. There's definitely 1 oxygen present, right? So 2 times 1, the 1 that's there, we end up with 2 oxygens. We're good. 4 sodiums on the left reacting, 2 oxygens on the left reacting, 4 sodiums produced, 2 oxygens produced, okay? That is ultimately the base of any sort of balancing. You have to have the same number of atoms reacting as you do being produced. Now, some more hints here is really watch, guys, that those formulas are correct. And I highlighted here for Hofbrinkel. Hofbrinkel are those diatomic molecules. H2, O2, F2, Br2, I2, N2, and Cl2. Do not lose track of those. The states of matter I mentioned are on the periodic table. Please also recognize we have a couple other exceptions there. I've mentioned them many times before. Sulfur is S8 and phosphorus is P4. It is your responsibility that when you see those elements singularly part of a reaction, they have to be expressed. S8, P4, and then the diatomic ones. All right, you can, next little hint here, use coefficients. You can add in coefficients, ones that weren't there, okay? There's always a 1, but perhaps it needs to be something different to make sure that the different elements are balanced. These last three here, this A, B, and C, can be quite helpful. You may find this useful to start with the atom with the highest subscript. That's the little number. And I find out of any of these, this one's the most helpful, B. If a polyatomic ion just stays together as a reactant, as a product, you might find it easier to just keep it like that. Like, for example, if you've got phosphate mixed with one thing on one side, and then you've got on the other side as a product, phosphate still there mixed with something, keep it all together. Don't try to balance it as a phosphorus and an oxygen. It just saves you some time. Any elements, last, what I mean by that is any elements that are all by themselves. Like let's say you have just oxygen all by itself, O2 gas. Do that last, makes it a lot easier, okay? This is important too, guys, is that the coefficients have to have that simplest whole number ratio. I mentioned that before, and I mean that if you can reduce it, you should. What if you can divide every coefficient you put there by 2? Well, you better do that, reduce. And like I mentioned, no fractions, no decimals. We need whole numbers, okay? So 1/2 is not okay. All right, here we go. Let's give this a try. Like I said, I know it's been a while for many of you since you have done this. Okay, sorry, when I change this to a PDF, I lose my arrows. So first things first is you need to correctly predict formulas. And if you mess that up, the balancing isn't going to happen. Now, this is a building block, guys. This balancing of reactions is something that you need in order to achieve the steps that we do later in this unit, and of course, in future chemistry courses. So yeah, your predicting of formulas is integral. Sodium, for instance, is a metal. And if you don't know that, you can look on your periodic table, but I think most of you do know. So sodium is a metal, it is a solid. How do I know that? Because when I look on here, I can find it, and it's yellow. Yellow means solid, right? It's not guesswork, it's there. Okay, sodium metal plus chlorine. Your mind should be going ding, 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 ding. Chlorine is one of those Hofbrinkel, diatomic, Cl2. If you don't write it like that, there's going to be issues. What state of matter is chlorine? Well, once again, come over here, find it, look for it. There it is, chlorine. It is blue colored, which means it is a gas. Some of these you'll have memorized, but if you don't guess. They're there for you to help you. Okay, this turns into sodium chloride. Your mind should go, oh, that's a metal and a non-metal. This is an ionic compound. So write out your charges so that you can correctly predict the formula. Na plus, Cl negative, that means we will get NaCl. Now here's the deal, guys. Any ionic compound that's produced without the presence of water, which this is going to be a solid at room temperature. Okay, I mentioned that earlier. Okay, if you stop here, you just got it wrong because you're acting like God. You just destroyed a chlorine atom. You can't do that, folks. You don't have the ability. There are 2 chlorine atoms going in, so you have to have 2 coming out. You cannot add a chlorine with a little 2 there. No. That's not okay. The only thing you have the option to do is to put a big 2 there, a coefficient. But notice what just happened. You have now made it that, yes, we have 2 chlorines going out, but you also put an extra sodium. So now we have 2 sodiums, 2 NAs. Go back over here, we've only got 1 over here, and that's not good enough. So same thing, we have to balance this. Put a 2 on this side. Always double check. 2 sodiums reacting, 2 sodiums produced. 2 chlorines reacting, 2 chlorines produced. Dun, da, da, da. This is now balanced. You must be in a habit to put states of matter, please. If you are answering questions without states of matter, you are probably going to get less than 50% on your assignment, okay? I'll tell you that straight off. This entire assignment, this whole week 7, and honestly from here on in, you must be aware of the states of matter, thinking about them, and actively trying to put in the correct ones. Okay, let's do the next one here. Aluminum chlorate, check it out, definitely an ionic compound. We have a metal and a polyatomic anion. So aluminum is Al3+, so we can build a proper formula. Chlorate is ClO3 negative. Oh, look, if you have those memorized still, this is suddenly faster. If you don't, well, it's going to take a while. Sorry, folks. Right from the beginning, I said, memorize your polyatomic ions. Get used to your periodic table. Makes things so much faster. Anywho, aluminum chlorate. There's no water present here, guys. So that means as an ionic compound at room temperature, this is going to be aqueous. If my pen wants to write. There we go. Oh, sorry, aqueous. My brain got ahead of me. This is going to be solid. And that's what I meant this time. Da-da-da. Room temperature, no water present. This thing is solid. It is going to produce, according to the question, aluminum, not aluminum ion, guys. Aluminum. What state of matter? Check your periodic table if you don't know. Aluminum solid. Chlorine is diatomic. You must write it as Cl2. On your periodic table, it's listed as a gas at room temperature. And oxygen, again, has to be written as O2 gas. Okay. Well, we've predicted the formulas correctly, but what about the balancing? Now, this is one where if we could, we would leave this chlorite intact, but unfortunately it gets split up. So it doesn't do us any good to balance it all together. That means we're going to have to separate things. Check out those oxygens. Oxygen, I would have 3 times 3. So 3 times 3 means I actually have 9 oxygens. Now here's where things get a little bit complicated. 9 oxygens over here. 2 oxygens over here. Can you multiply 2 by any whole number to get it to 9? No, you'd have to use a diffraction, right? A decimal. So if I can't multiply that by a number that will get it right to 9, then I'm going to have to get this 9 over here to be an even number. So that's your hint. If there's an even number 2 on one side, you're going to have to end up with an even number of atoms on the other side because you can't have half of atoms. Of course you can't. It's not like there's a half of a Mrs. Sakura, okay? Be logical with these guys. So I'm going to actually start by multiplying this whole thing by 2. That way, look what happens. We end up not with 9 oxygens, but with 3 times 3 times 2. So 3 times 3 is 9. Times 2, we have 18 oxygens. This is doable. I can get this 2 up to 18 by timesing by 9. Nice. All of a sudden, my oxygens are balanced. I got 18 of them on both sides. That's good. I started with that one because there was more oxygens than anything else. Now let's hope that the chlorines and the aluminums are a little easier. Look at aluminum. Super easy. There's 1 on there times the coefficient of 2. Oh yeah, we just have 2. So 2 on each side, done. Chlorine gets a little more complicated. Think of what we've got here. We've got 3 times 1, okay? 3 times 1, and then that's 3. Then you have to multiply by the 2. So 3 times 1 is 3 times 2, that's 6. However, it doesn't make sense to put a 6 here, because you can't forget about that 2, okay? So that means that what we're going to have to do is think what times 2 will give us 6? It's a 3. There we go, guys. It's a puzzle, like I said. I love this sort of thing. For those of you that don't, I know it's a little bit more of a headache. One thing you can do that sometimes helps people is make a little table. So you don't have to do this, but you can be like, okay, this is my reactants, this is my products. And then make sure you list them out and actually count them and check them. So for example, now we'd be like, okay, I got 2 aluminum, I've got 2 aluminum. And I've got my 18 oxygens and my 18 oxygens. Okay, I'm good. And I've got my 6 chlorines and my 6 chlorines. Check, check, check. Right? It forces you to see them. If I'd had a 6 in front of that product producing, I would have caught it and be like, oh, I just made 12. Oh, I made a mistake. And then you can go back and double check your work. Okay, anyway, let's do the third one here. Butane plus oxygen. Now, butane on your actual sheet, I give you the formula for it. I wouldn't expect you to know the formula of this, guys. Butane is C4H10, and it is a gas at room temperature. Like I said, that's on your notes. Oxygen, though, I would expect you to write it diatomic, O2 gas. I would also expect you to know that carbon dioxide at room temperature is a gas. It's a very familiar molecular compound. And water vapor, hint, hint, it's vapor. Vapor means gaseous. So this is H2O gas. Okay, Balancing this one, where are we going to go with it? Well, similar process again, and that let's start with the one with the highest coefficient. So let's start with this hydrogen, 10. Now I want you to stop and think about this. I have 2 hydrogens being produced. So logically I would put a 5 here because then I'm at 10. But here's the problem. Look what that does to oxygens. 5 oxygens. Reacting, I've got 2. I cannot multiply 2 by anything and get it to 5. That's a whole number, right? I could multiply it by 2.5, but no, we can't use a decimal. So that's an issue. So remember what I said before. If you have an even number on either reactant or product side, the only way the multiplying of coefficients is going to work is if you have an even number on the opposite side too. 5 is not even, 5 is not going to cut it. That means that we're going to have to go back and play with these a little bit. The 5 doesn't work. So instead, what would work is the next multiple, which would be 10, which means I need a 2 here. Now we have an even number of oxygens, 10 of them. Now we're cooking, okay? 10 oxygens, I can multiply this side by 5. 5 times 2, I've got 10 oxygens. Woo-woo, we're good. Notice the hydrogens worked out. 2 times 10, I've got 20 hydrogens reacting, 20 hydrogens being produced. We're good. Let's finish it off here. And, oh, I just saw something. Did you see what I missed? Look back to it. Do we actually have 5 over here? This happens all the time, okay? That 5 works right now, but look what's going to occur as soon as we play around with the carbons. 2 times 4, 8 of them. Uh-oh. There are 10 oxygens in water, but I now have 16 oxygens in carbon dioxide. That's okay. There's nothing wrong with this, but you just have to make sure that we have the correct total number reacting as I have produced. We have a total of 26 oxygens being produced now. I only have 10 at this point. So I'm going to have to go back and say, nope, there's not going to be 5. I need to have a total of 26 instead. What times 2 is 26? 13. Now this works. 13 times 2, 26 oxygens, we're golden. 8 carbons, we are officially balanced. Okay, puzzles, like I said, back and forth, play around. Highly recommend you do them in pencil because chances are you're going to be erasing a bit as you play. And it's okay that they are works in progress. It's okay that you're going back and forth like, oh, no, it's not 2. I have to double that, back and forth, no problem. Okay, let's check another one here. Moving on, put my arrows in. There we go. Okay, check it out. Scandium. It's not mixed with anything else. It just says scandium. That means that it is SC solid metal. Look at the next one. Copper 2 sulfate. Ionic compound, which means this is going to be copper 2 plus sulfate SO4 2 negative. In the assignment, I'm really clear for you if something is aqueous or not. This one is because this type of reaction wouldn't happen if it actually wasn't a dissociated copper 2 plus SO4 dissolved in water. So that means this is copper 2 sulfate aqueous. Like I said, on the assignment, I'll make sure I help you out with that, okay? So we keep going and we end up with copper metal, just right, copper by itself, and scandium sulfate. So again, think about the charges. Look on your periodic table. Scandium is a 3. Okay, sorry if there's a little bit of a blip between here. I had to start a podcast over here again for a second. Okay, so we're moving on into D as the example, guys. So scandium is a metal on the periodic table. So we have scandium solid. Now when you're predicting the formula for copper 2 sulfate, you'll be taking this as copper 2 plus sulfate SO4 2 negative. The positive 2, the negative 2 are going to balance, which means we have copper 2 sulfate, just like so. Now this is something I'll specify in your assignments, but this would be aqueous because a reaction like this with a metal and an ionic compound won't happen unless it's in aqueous form, okay? So Keep going. Copper, of course, is a metal, so copper is solid. When we're predicting the formula for the scandium sulfate, we need to look at the charges. Scandium is a 3+. Sulfate, as you know before, is SO4 2 negative. This is definitely a drop and swap type scenario. We'll have scandium 2 bracket SO4, 3 of those. Now what about state of matter? You can't assume aqueous. Yeah, there's water present, but how do you know what it's going to be? Well, this is where we go back to our solubility table. Look at the anion first, right? Here is your sulfate. So at that point then, where is the scandium going to come into play? Well, look for it. As it turns out, it is in the most section, which means we have a situation that's going to be aqueous. Oh, I'm looking at the notes and I see I wrote it as a solid. Oh, so if you have the notes in front of you as the PDF, change it. Should be aqueous. Oh, we all make mistakes sometimes, right? Half the battle is catching them. Anywho, so it's going to be aqueous. If I can write that in over here. Last step is the balancing. These are easier. You have 2 scandiums being produced, so we need 2 going in. You have 3 sulfates. Notice I'm keeping it as a polyatomic ion because that polyatomic ion, SO4, is kept intact as a reactant and as a product. It's way easier to balance it that way than to split it up into sulfur and oxygen. Anyway, we've got 3 sulfates being produced, which means I need 3 sulfates to be reacted. I've now messed with copper, so I've got 3 coppers being reacted. I need 3 coppers be produced. Dun, da, da, da. There it is, guys. Alrighty, very last one here, hydrochloric acid. The acids will come back to haunt you. You should know these formulas, be able to figure them out. This is classical naming. The hydro means that it is hydrogen mixed with a single anion, HCl. Acids are always aqueous, so HCl aqueous, plus barium hydroxide. Same thing, I will be clear about this on the assignment, but you need to assume that if we have this type of reaction, and when we do reaction types, you'll know what kind it is, that these are in solution. So we have barium 2+ with hydroxide negative. That means drop and swap will work good. You will need to have 2 hydroxides, aqueous. Okay, keep going. We'll produce water. Well, that's a no-brainer. However, I'm going to give you a hint when it comes to balancing. Instead of writing it the classical H2O way, I'm going to write it as HOH. A lot of times this is way easier so that you can see it's almost like this is a hydroxide, sound familiar, with a hydrogen, okay? Easier, trust me. Barium chloride, on the other hand, we're going to have the Ba2+ mixed with the Cl negative, drop and swap. We will have BaCl2. Never assume solubility. Always take the time to check it. When we check it, find your chloride ion. It's right here. Barium fits under most. It is not listed as copper, silver, mercury, Hg2+. That's a weird mercury one. Lead 2+, tellurium. Nope, none of those. So that means it is aqueous. Okay? Last bit of balancing. Here's that hint. There are 2 hydroxides. Well, this is like hydroxide. See, if you write the water that way, it's easier. So I'm going to have to multiply this by 2. Look what happens now. We have a total of 4 hydrogens, okay? And barium hydroxide, there's only 2 hydrogens. I need 2 more to get to 4. How am I going to do that? By putting a 2 in front of the HCl. Now look what beautifully happened now. I have 2 chlorines and there are 2 chlorines produced. It all worked out. We're up to our 4 hydrogens total on each side, 1 barium on each side, 2 chlorines, done and done. All right, guys, when it comes to homework, there's a number of questions you can continue on. You can do all of number 3, all of number 4 to practice this balancing, and hopefully it will re-cement in your brain from when you first did it in Science 10. All right, I'll see you at the next podcast.